What's up, YouTubers? So I was cleaning my shop and I got to thinking that my previous video was 7018 where I talked about rod ovens and safe storage and how to prevent moisture pickup, all that kind of stuff that was covered in that video. That kind of only touched the surface of the whole issue. And I thought, well, why wouldn't I do a whole video discussing the rod ovens, the hydrogen embrittlement, and just, I guess, the whole broad category of that and why 7018s are used over other rods like 7014 and 7024 or even like 6013. And I think there's a lot that we could all learn from this, myself included. I had to do a fair amount of reading for this to try and get my bearings straight on, and at least be pretty accurate. But yeah, so let's dive into it and see where this rabbit hole leads us. So this is probably one of the most confusing topics with stick welding, and I gotta admit, even for myself, I had to do a fair amount of research to really grasp what was going on with this. And it comes down to hydrogen embrittlement and why 7018s in specific need to be kept in rod ovens or used directly out of a pack. And there's all sorts of rules and speculation. And I gotta 100% admit that there's so much misinformation out there on the internet. Like, everyone has different ideas of how to deal with the moisture pickup issue. Like, there's just so much misinformation, and it's kind of like there's incorrect, there's a gray area, and then there's correct. This is hopefully gonna knock the dust off of all of that to where you can make your own opinion on what I guess is relevant to you. And it all comes down to 7018 and whether or not you need to keep it in a rod oven. Like, this particular rod says it's MR, which means moisture resistant. Do you need to keep these in a rod oven? Do you need to bake rods like this that do not say moisture resistant anywhere on them and just says 7018? Do these need to be in a rod oven? Like, so many questions, and that's what we're gonna get into. All right, to start things out, let's talk about what a rod oven is. These are all rod ovens. Now, they function slightly different, but they all serve kind of the same purpose, and that's to keep the rods at a specific temperature. Now, most of these are just kind of conditioning ovens, where they can keep the rod at 250 to say 350 degrees. So they're really for like long-term storage, and they're not designed for rebaking. Now, the bigger barrel ones, I believe, will work for rebaking. And what rebaking is that if a particular rod has been out in the atmosphere for long enough, and I'll talk about those timelines next, but over a certain period of time, you have to rebake it. And rebaking the rod requires an elevated temperature of 600 to 700 degrees for, I believe, an hour minimum. So those ovens can get to those kind of temperatures to bake all the moisture out of the rod that is absorbed into it, basically. And that's the primary difference. Is the smaller ones are really only meant for stable conditioning for an extended period of time for storage purposes, and less so to bake out moisture that's absorbed into the rods, if that makes sense. So now let's talk about the baking procedure. This is directly from Hobart/Miller. They talk about for 7018, 8018 and such, the storage of the rod should be 250 to 300 degrees steady. And then the actual reconditioning, where you would take rods that have met the exposure time limit and exceeded it, you would bake those at 500 to 800 for 1 to 2 hours. So that's the general gist of it. Now, you would have to have a rod oven that could get to that temperature to meet that requirements. And like I said, most of the ovens that we saw are mainly for storage, so much lower temperatures. So now the next question that you need to be asking yourself is, well, at what point is it safe to use the electrodes? When do they need to go in an oven? And well, that comes down to a number of factors. So here we have two different types of rods. We have the MR rods with the red top and the Lincoln can, and then we have Hobart rods in a plastic container that's taped shut. Now, code says if you take a 7018 rod out of a hermetically sealed package and pull it directly out of there, you typically by code have about 4 hours to use that rod, and it meets the low moisture requirements for code. Now, the MR rods and certain specified code rods, you may have upwards of 8 or more hours that you can have it exposed to the environment, meaning like in a rod pouch or something, before it no longer meets the low hydrogen specification. So it really comes down to, on part one, the rod you're using. The second part is that, well, what container is it in? The Hobart rods on the left are specified as H4R, so hydrogen diffusible levels that are specified. The problem is that a hermetically sealed container? Honestly, I would say no, because the Lincoln is a sealed, vacuum sealed can with a pop top on it, and like ESOB rods that I have are vacuum packed in a plastic wrap package. Those are hermetically sealed. I don't know that by code that those Hobart rods would be considered. I mean, maybe they are, maybe they aren't. And you're probably wondering if this is a hermetically sealed container. Well, it's pretty simple. According to the American Welding Society, who really specifies all of these codes dealing with 7018 and that most industries follow, that in order for it to be hermetically sealed, it would have to be vacuum packed or sealed in a tin with a pop top to where moisture cannot get to it once it's sealed. And once you break that seal, you basically, according to the American Welding Society, have 4 hours with most 7018 rods to use them, or during that period of time, you have to put them in a rod oven at about 250 to 300 degrees. If you exceed that 4 hours that they're out of that package, say you had them on your table or in the pouch or whatever, after 4 hours, and it depends on the rod and code, it may be upwards of 8 hours depending on the rod, you have to rebake the rods at between 600 and 700 degrees, again, depending on code, for at least 1 hour to be considered low moisture again. And now you can only, by code, generally rebake the rods once before they must be discarded. And that is due to the flux deteriorating after numerous rebakes at higher temperatures. The flux just isn't good anymore. These are all basic code. You may work for a company or do a job where they specify that any rods out of any package immediately go in a rod oven for, say, 2 hours, and that you take them out, put them in your pouch, and if you don't use them in 2 or 4 hours, they get discarded. Like you go work at a nuke plant or something, and the codes may specify that, and for good reason, and that's because of the liability. It may not even with the modern rods be necessary to do that, but just, it's one of those things like, is it really worth reinventing the wheel when there's an extreme amount of risk involved? I think the answer is no in that case. Now, I understand, us as home welders, we're not building nuclear reactors or stuff to go to the moon, so you might feel that a lot of this isn't relevant to you. And for the most part, you're probably right. However, the point of this is to get you guys to understand what hydrogen embrittlement is and why certain things are done in a specific way so that you can make educated decisions on what you need to do as a welder. So let's go and get further into this rabbit hole. So now that you understand what rod oven is, which is pretty simple, but hopefully that brought you up to speed on that, we need to talk about something that I kind of, in a lot of videos I mention, but I don't really go in depth on, and that's what's called welding code. Now, when you work on big jobs, like say you're gonna weld some piping in a nuke plant or a power plant, or even pretty much any kind of industry, like on a bridge, municipal work, whatever, there's specific welding codes that apply to what you're doing. it's not as simple as like anyone can just go sign up and then go weld on a bridge without meeting certain, testing criteria, like they're certified welders, which all that means is that they've passed testing that is comparable to the work they're actually doing. So the certification merely says that at that test day, they were capable of doing the welds to specification. Well, you and I that work in our home shops, we're not certified, okay? And not only that, a lot of the work that we're doing, almost all of it probably is not code work. Basically, it is not government required or particular employer required to where you have standards you have to meet. So a standard could be this amount of porosity per feet of weld. It could mean this amount of undercut per weld. It could mean any number of things like under penetration. It could mean in passing x-ray. It could mean dye penetrant, all this testing. We're in the home shop simply making welds and hoping if we do a good job, stuff stays together. We're not doing all the testing. We're not certified, right? Well, with jobs that require certifications and high liability jobs, not only are the welders that are doing the work need to meet a specification on their capability, but all the materials involved in that job also have to meet specifications. So everything, like, let's just simplify it. A city wants to build a bridge, right? Right in their downtown area. Anyone who shows up to weld on that bridge has to have a certification that says that they're competent to weld that type of material in those circumstances. And again, this is in theory, but it's in practice, it's pretty much the case. You're not going to find too many unqualified welders welding on bridges, okay? And not only is that welder that's doing the actual welding on that bridge have to be certified, the steel that that bridge is made out of is certified to testing standards. The design of the bridge is signed off by an engineer, and that his signing off is based on either his own design and testing with software or based on like general rules in industry. Like every part of that job, in theory, has had numerous testing certification stamps all the way down the line. That includes your welding rods. Now, a lot of bridges today, I'd imagine, aren't stick welded anymore because of the efficiency of it. Not to say that they're not, but I would imagine not. Well, let's say they're stick welded. The rods themselves that are used to build that bridge, such as this rod right here could be, are certified to meet a very specific standard. And again, it goes back to liability. This particular rod is designed to deposit a weld of known quality and test results if certain criteria are met. One of those criteria with 7018 is that it's held in a rod oven, and the purpose of the rod oven, like I previously said, is to lower the moisture content of this flux so low that the risk of what's known as hydrogen embrittlement is zero, or as close to zero as you can get it. So if you were to use a rod like 7014, 7024, any number of rods, hydrogen embrittlement could be an issue because those rods, like especially your 60 series, like 6010, those have moisture in the flux when they're made. And if you're gonna have a hydrogen embrittlement problem, you can imagine a rod that literally has flux the day or has moisture in it the day it was made and is designed to run with moisture in the flux, that could cause a huge problem. So really, the purpose of 7018 is it's a rod that meets code for structural jobs, and part of the reason it meets code is because the moisture content is so low that hydrogen embrittlement is not going to be a concern. Now let's talk about hydrogen embrittlement a little bit. All right, so hydrogen embrittlement is basically the reduction of ductility due to absorbed hydrogen. Now, I'm going to take a lot of what I'm talking about now directly from Miller's website, Miller Electric, as well as the usual sources, Wikipedia. Not the most reliable, but they do have a lot of good collection of information there. I will leave links to all of this information down in the description, okay? But hydrogen embrittlement is the reduction of ductility due to absorbed hydrogen. One of the things you need to understand is this metal, which appears solid, heavy, and kind of one piece, on a molecular or atom scale, there's things moving around in activity. It's just our scale, it appears solid. Well, hydrogen is a very small molecule, apparently, very small, and it can move and diffuse into something to us that appears as a solid, and it can diffuse and move around in this like it basically doesn't care. Now, you can see I can't diffuse into this. It's a solid to me, but like I said, hydrogen doesn't care. So the danger is that when you take rods like 7018 or any other welding rod that has diffused hydrogen or moisture in the flux, and then you weld metal, you can impart that diffused hydrogen into the solidifying weld and solidifying the welded area, which can reduce the ductility of the material and promote cracking. Now, I have pictured here a weld nugget, so that's like these welds on this plate. And what most commonly will happen during hydrogen embrittlement is as you lay that weld down, okay, which is depicted here, hydrogen will diffuse in that weld to the nearby area, which hydrogen diffuses via heat, okay? Well, if this weld nugget here is hot, it's likely to drive that hydrogen into the metal. And in this heat affected zone, it's very common to get what's called under-bead cracking. That's where a crack will actually start not in the weld you deposited. However, it's going to start right under the bead. And I'll put up pictures now to show what I'm talking about. But you will get an under-bead crack. And that is due to the hydrogen escaping the welded area by diffusing into the solid, colder base metal. And normally, under-bead cracking or hydrogen embrittlement cracking happens fairly fast. So in most cases, it's a fairly fast process. It's not like, 10 years later, all of a sudden it cracks. I mean, that can happen, but most of the cracking can happen fairly immediately. The issue is you may not see it. If you don't do X-ray testing, and maybe even X-ray might not even show it, but if you don't test it, how do you know that it's there or you don't know? Well, that's a huge problem, because you can imagine if you have a weldment, like say this is a weld and it goes all the way through, multi-pass weld, and it's cracked underneath, you have no idea, well, what's going to happen if you stress that? It's going to fail. And that is where hydrogen embrittlement is a huge risk, especially on structures that need to support a lot of weight, like bridges, or even in high strength piping, anything along those lines. The risk is very significant to having hydrogen embrittlement problems and under-bead cracking and essentially weak welds. That is why 7018 rods like this and these up here were created, and then all of the codes related to the storage and baking of them exist, is because it created a method to safely weld higher strength steels without risking the hydrogen embrittlement cracking. Now, with that said, there's a couple things that I want to talk about, and that's what type of steel does this commonly happen in? Well, this steel right here, which is typical A36 steel, what your local steel mill will sell you. It's cheap steel. It can be found most commonly in C-channel and angle iron. Not to say all angle iron or C-channel is A36, but very common. Cheaper steel. A36 is around 79,000 PSI ultimate tensile strength. Hydrogen embrittlement typically happens, from what I've found, above about 140, 150,000 psi tensile strength and above steels. This is well below that. The risk of this having hydrogen embrittlement is very low, okay? Almost non-existent, and that is why you can weld A36 steel with rods like I got here, like 6011, 7014, and you're not really gonna risk hydrogen embrittlement. All of these rods, 6011, 7014, all of those rods impart, especially 6011, impart a ton of moisture of hydrogen into the weld, okay? And yet you don't really hear many failures of stuff like this, and that's because hydrogen embrittlement, for the most part, does not affect low strength steel. But there's a caveat to that, and that's, like you saw in a video, I welded some of these hooks on, and even like this D-ring over here, but let's focus on this hook. This is a forged part of unknown alloy. This, for all we know, could somehow be a mixture of alloy with a high enough tensile strength or a composition that would make it susceptible to hydrogen embrittlement. And although the steel you welded this to might not be susceptible, this in itself could be. And how on earth are we going to figure this out? Okay, an excavator you work on, like say you had to do a welding repair to an excavator or a skid steer. How do you know what steel that they're using? You might not. You might be able to contact them. You may be able to find information, public information about what it's made out of, but you and I as home people, we don't know. And if there's one thing that's not worth the risk is anything with liability, anything where it's unknown but it's probably of high strength, such as this, you should probably be smart and say, you know what, it's probably not worth the risk of hydrogen embrittlement and running rods like your 7014, your 6011 on something like this. You could run into an issue with that. And it's also worth noting that the Rockwell hardness, I can't remember what the exact spec is. I'll put it up in a picture now, but I believe it's around 32 or so Rockwell hardness, and above steels are also prone, and that's regardless of their tensile strength. So that's something else to be aware of, that the hardness of the material you're welding will also play a role in hydrogen embrittlement, from what I've read. So we talked about what hydrogen embrittlement is. We talked about the materials it affects, and I didn't mention, but it does affect things other than steels, like titanium and certain coppers. I mean, when you read the articles, it's a wide variety of materials it can affect. And we talked about it primarily affects higher strength steels. Now, there's ways to combat it, because obviously higher strength steels are welded all the time. So let's talk about that a little bit. And this is a home gamer. A lot of this isn't going to be relevant to what you do, but it's still worth listening to, because there's always stuff that you can learn, and the more you know, the better off you are. Trust me on that. So using a different process. Now, the flux on the 7018 is prone to moisture pickup, as are all rods. So by switching to a process like maybe TIG, you can significantly limit the amount of hydrogen that can find its way into the weld pool, because you're not dealing with a flux anymore. That's a possibility, okay? By using certain types of wire with the MIG and spray arc and that type of process, you can also control the hydrogen input. The other thing you can do, and it's very common on higher strength steels and higher strength pipes, like on pipelines, is they preheat the material. You have to remember, like I said earlier, this material to us is a solid, but to hydrogen it might as well be Swiss cheese or a sponge. It can just go right through it like it doesn't exist. Well, prior to welding, if this was a high strength piece of steel and we heated it to, I don't know, 200 to 400 degrees, somewhere in there for a certain period of time, any hydrogen that's in it would diffuse and it would leave the material. it would be prepped for welding, and then you weld it, and then you post heat it. So typically when they preheat the material, weld it, and then they keep it hot for any number I read, 24 to 48 hours, 200 to 400 degrees. So the post heating serves two purposes. It keeps the material from cooling fast because that shrinking, remember, this whole area is under tension after welding because that weld wants to shrink as it solidifies. Well, by keeping that whole welded area at say 200 to 400 degrees for 24 hours after welding, that's going to limit how much shrinkage there is. It's going to limit, if there is any hydrogen in it, it's going to allow that to diffuse out of the area so that it doesn't exist, that when it becomes room temperature, that the stress causes cracking. So the post and preheat on high strength things like piping, hugely important. Not only is using rods that have low hydrogen to begin with, but that pre and post heat, very important. So I know you're probably wondering as a home gamer, well, if I just torch heat this steel, will that work? Well, yes and no. You have to understand that if you're using like a MAP gas or propane torch on something like that, that torch in itself is going to impart hydrogen onto the steel, okay? You at home, unless you're using like an induction heater that excites the atoms in here and it creates heat, unless you're using an induction heater, honestly, using a torch, very minimal gain for you at home. You know, if you're going to weld high strength steel at home, which I've done a fair amount of that for like a tool and die shop or something, you want to do the pre and post heat with either an oven or if you're going to use a rosebud, then you got to be very specific on your pre and post heat temperatures and all of that. You know, you really need to know what you're doing with that because you can run into serious cracking issues with if you let it cool too fast, you let it get too hot between passes, etc. That's a whole nother topic for another video. I need to get back on topic here. So as a home gamer, there's not a whole lot that you're going to be able to do, and doing something in the hope that it's going to have an effect, you can cause more damage than good doing that, okay? So the post heating, again, controlled situation, propane torch, not going to cut it, okay? What you can do as a home gamer is if you're welding something like this hook of an unknown but likely high strength, what you want to do is you want to bake your rods out, your 7018 rods, in an oven in order to get any of the hydrogen out of it, and then you want to weld it with that rod. I know, you know, these things in D-rings, all this stuff, you know, your farm hand has welded those since the crack of dawn 100 years ago with 6013 and never had one fail, and I totally get that. But if you're going to do something that likely requires strength, the proper way is to use 7018 and cook it off in a rod oven or use it directly out of the pack. So that whole video so far is quite the mouthful, right? And you probably learned something, maybe you got a little bored, and I don't like, you know, all this book smart stuff. You know, I want to teach you guys how to build stuff so you can gain confidence and make the world a better place, maybe, who knows? Or just annoy your neighbors by welding on a fart cannon on your Honda Civic, I don't know. But the whole point of me sharing all of this is so it's a tool for your guys' toolbox. If you understand why certain things are done, it's going to help you become a better welder. And you can also apply that logic of figuring out how things work to a lot of other things besides welding. And that's kind of the point of me doing this. But anyways, to kind of finish up this video, I just wanted to talk a little bit more about these other rods that I have here, which is like 6011, your 6010s, your 7014s. These rods, which you probably still use or have used, you know, 7024, any of those, 6013, all of those rods are not low hydrogen And when you weld with them, they introduce hydrogen into your welds and into your base metal. So if you've been welding a ton of stuff, you've actually unknowingly been putting hydrogen into it. So if you're welding low strength steel, excessive hydrogen that these rods will put in there really isn't a huge deal. So when it comes to using 7018 as a home gamer, even technically, if you were to not follow the code on it and say you open up the container you used, pull like 3 out, seal it, and then leave it, and you don't rebake it or you don't put them in a rod oven, as a home gamer, you're probably going to be just fine. Now, I have to say probably, because if you're welding high strength steel or something that of unknown strength and it happens to be high enough strength steel that hydrogen embrittlement becomes a problem, guess what? By not using the correct tool for that problem, you're going to create a new problem, and that's cracking due to hydrogen embrittlement. But for the most part, you're fine. This, you have to look at 7018 is an awesome tool in your toolbox that if you use rods straight out of a hermetically sealed container or out of a rod oven, and you need to do a repair on something that's higher strength, and you follow procedure for that material, you now have the capability of welding a higher strength material and actually having the weld function and not crack. That's an awesome tool, because believe it or not, I mean, you're going to find higher strength steels all the time, especially if you're a farmer and you're repairing stuff on, you know, I don't know, a plow or some kind of claw, any number of things that you might be doing. By using the correct rod that does not impart hydrogen into that weld, you can make a much stronger weld than with any of these other rods like your 6011s, your 7014s, because 7014, even if you bake that in a rod oven, it's still not considered low hydrogen, and it still may impart hydrogen into your weld. The other thing worth noting here is that I and most welders really like the way 7018 welds. The puddle's very clearly defined. It has very minimal spatter. Like when you compare it to 7014, I find the puddle for 7014 very difficult to see. It's very prone to have that puddle run ahead of your rod, and you get slag inclusions, I find, much like 6013 and 7024, especially like 7018 is so easy to run uphill, vertical up, and overhead, much easier than 7014, I find, and 6013. So anyways, it's just a really easy rod to run, especially out of position, very low spatter, very clean looking welds. It's definitely something you want to get good at. And my hope is that everything you learned in this video gives you an idea of why certain things are done a certain way, and you now know what you have to do if you're welding higher strength steel or you want to make the strongest welds possible. And let's face it, if you get into welding enough to where you're doing a lot of repairs, like as, you know, a traveling like home handyman welder type person, you're going to want to get a rod oven. There's really, you know, 150 bucks, you know, not a big deal. Or get smaller packs. Like this thing here is probably like 40 bucks for a pack. That's pretty pricey, but you can get the 4-pound ESOB packs for like 17 bucks or so, and just skip the rod oven entirely. You know, it's not a big deal. Again, it's just a tool in your toolbox to make really strong welds on higher strength steels. So that's all. So hopefully you guys learned something. If you have any comments, questions, concerns, feel free to leave them in the comment box. And, you know, for all I know, I made some errors in this video, and if so, I will go back, correct them, and then re-upload it, because my goal is to keep you informed as possible. Anyways, thanks for sticking around. Hopefully you learned something. Till next time.